Welcome to The Explainer. You know, sometimes the biggest ideas have the smallest beginnings. Today, we're going to talk about how a simple toy, one that's 2,000 years old, actually holds the secret to leaving our planet. It's an incredible story. So, let's dive right in. So, take a look at this. Believe it or not, our entire journey to the stars, it pretty much started right here, with this spinning, steam-powered sphere from the ancient world. Yeah, it might just look like a clever little toy, but the idea it's demonstrating, that's the core principle that makes all of spaceflight possible. Seriously. So to really get how we launch these absolutely massive rockets beyond our atmosphere, we've got to go back, way back. We need to get a handle on a core idea that's, well, it's been hiding in plain sight for thousands of years. And here it is, the big one, reactive thrust. You've probably heard of Newton's third law, right? For every action, there's an equal and opposite reaction. Well, this is it in practice. And here's the part that trips a lot of people up. It is not about pushing against the air. Nope. It's all about throwing mass, like super hot exhaust gas, out the back really, really fast. And that action of throwing stuff backward pushes the rocket forward. That single, simple idea is the thread that connects that ancient steam toy all the way to the most powerful rocket engines we have today. Okay, so how do we get from that simple principle to, well, to the kind of brute force you need to actually leave the planet? The answer is pretty wild. You have to create, and then somehow tame, an absolutely massive, continuous explosion. And this is where rockets are just different. Think about a jet engine on a plane. It has to suck in huge amounts of air from the atmosphere to burn its fuel. A rocket, it's a completely self-contained system. It carries everything it needs with it, both its fuel and its own oxygen source. And that, right there, is the whole reason it can work where there's no air to breathe, in the vacuum of space. I want you to just think about that phrase for a second. A controlled explosion. I mean, that's the whole ballgame right there. That's the fundamental challenge. The trick isn't just making a giant explosion. That's the easy part. The genius is in managing all that insane energy and pointing every last bit of it in one single direction. And this is how they do it. This bell-shaped nozzle is just a brilliant piece of engineering. It takes all that chaotic, violent energy from the explosion and channels it perfectly. It squeezes and accelerates all that super hot, high-pressure gas until it's moving at incredible supersonic speeds. It really is like pinching the end of a garden hose to make the water spray out faster. Just, on an absolutely astronomical scale. Okay, so we've got our core principle and we've got the shape of our engine, but this brings up a huge problem, a really fundamental one. How do you keep a fire burning where there's no air? And that's the challenge, right? This is what separates a rocket from literally every other engine we use here on Earth. You remember learning about the fire triangle in school? You need fuel, you need heat, and you need oxygen. Well, in space, that last one is kind of missing. There's just no oxygen to be found. So what's the solution? Well, it's actually incredibly clever. You just bring your own oxygen with you. It's packed into a special chemical called an oxidizer. So a rocket isn't just carrying fuel, it's carrying everything it needs to create and sustain its own fire, anywhere. And engineers have basically come up with two main ways to pack this fuel and oxidizer combo. On one hand, you have solid propellants. Think of these like a giant firework. They're simple, they're super reliable, but once you light that fuse, there's no stopping it. It just burns until it's done. Then you have liquid propellants. These are way more complex, but they give you a ton of control. It's more like a blowtorch. You can throttle them up and down, shut them off completely, and even restart the engine later. Super useful. All right, this is where things get really tough. We're now at the single biggest challenge in all of rocketry. I mean, it is a concept so demanding, so totally unforgiving, that engineers have a special name for it. They call it a tyranny. I mean, have you ever really looked at a rocket sitting on the launch pad? It's kind of absurd, right? It's basically a gigantic fuel tank with this tiny little capsule perched way up on top. Well, there's a very specific and, honestly, a very punishing reason for that. It all comes down to this really vicious cycle. See, to go faster, you need more fuel. Simple enough. But that fuel has weight. A lot of weight. So now you need to burn even more fuel just to lift the weight of your fuel, which of course adds more weight, which means you need more fuel. You see where this is going. It's this punishing feedback loop, and it's all governed by something called the mass ratio. It's actually the whole reason engineers invented staging, where they drop off the empty fuel tanks along the way. It's a clever trick to try and cheat this absolutely brutal equation. And when you look at the numbers, they're just staggering. For a rocket that's trying to completely escape Earth's gravity, almost all of its weight at liftoff is just propellant. We're talking something like 97%. That means only a tiny 3% is everything else: the rocket's structure, the engines, and the precious payload it's trying to deliver. It's incredible. So, to fight this tyranny of mass, engineers are completely obsessed with one thing: fuel efficiency. In the world of rocketry, they measure this with something called specific impulse, or ISP for short. The easiest way to think about it is like a car's miles per gallon. The higher the ISP, the more thrust, more oomph you get out of every single kilogram of propellant you burn. And that means you can build lighter, much more effective rockets. Okay, so let's recap. We have our engine, we have our special fuel, and we have a very, very healthy respect for the mass problem. So what does it actually take to put all of this together and complete the mission, to actually leave Earth? When you boil it all down, everything we've talked about, the reactive thrust, the special fuel, fighting that mass ratio, it's all in service of one single goal: achieving absolutely incredible speed. The entire mission of a launch vehicle is to get its payload going fast enough to hit two very specific, very important speed limits. First up is orbital velocity. A rocket has to hit about 8 kilometers per second. That's fast enough so that as it falls back to Earth, it keeps missing. It's continuously falling around the Earth. But to break free from Earth's gravity entirely, to head out into the solar system, you have to go even faster. You need to hit a blistering 11.2 kilometers per second. That's escape velocity. And, mastering all these principles, it hasn't just been some cool science experiment. It has literally unlocked space for us. It's given us everything from the GPS in our phones to our daily weather forecasts. It's what allows us to explore other planets and to peer into the deepest, oldest corners of the universe. So when you think about it, we've taken a simple 2,000-year-old idea about pushing something one way to go the other, and we've turned it into the master key that unlocked our entire solar system. We've figured out the physics of escape, which really only leaves one big question. Now that we have this incredible power, where should we go next?